Section 4.2 is basically taking some time and just listing off some different types of forces that we'll be using a lot in Chapter 5 and then moving onwards. So the first type of force that we'll talk about is weight. And the way that we're going to use the word weight is it's going to represent the force of gravity pulling down on us from the Earth. Our abbreviation for it is going to be little w, and it's going to have an amount, a magnitude, and a direction. So it is a vector. All forces are vectors. If you get a question that says, what's the force? You should give an amount and a direction. Okay. The amount of it is going to be mass times the acceleration of gravity, which was little g, 9.80 meters per second squared. And mass is the amount of stuff in your body this acceleration of gravity kind of is a description of how hard gravity is pulling down on you. Like if you're on the moon where gravity is weaker, G would not be 9.8. We would plug in a different value. So since we're going to be working on the surface of Earth, we'll be using the 9.8. So if I had more mass, gravity would be stronger and pull down on me. So just be careful to keep track of your units. And that'll help you keep mass and weight separate. Mass is in kilograms, and weight is in newtons. So let's do this. Weight is mass times the acceleration of gravity, and its direction is always going to be vertically down. Next, we're going to do a pushing or pulling due to a spring. We'll call it the spring force. A spring always wants to kind of return to its natural length. We can also call it its equilibrium length. So if you stretch a spring, it'll try to pull you back. If you compress a spring, it'll try to push you back out. So maybe I can try to sketch that. Maybe this is a spring's natural length, and we'll attach it to a block. And then somebody took the block and squished it into the spring, push, 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 push. So what's the spring going to do? The spring is going to push rightward on the block. So you can see that it's going to push back towards its original length, its equilibrium length. And if somebody were to grab the block and pull it out here and extend the spring, then what the spring would do is the spring would be trying to pull left on the block. Our abbreviation for this is going to basically be an F for force with a little SP. And it's a force, so its units are going to be in newtons, just like all the other forces. So let's quick sketch on here the amount of compression from its original length, or the amount of stretch from its original length. And so we could call that delta x. And then we could say that the spring force has the amount of K, which I'll define in a second, times the amount of displacement, and is always going to be in the direction kind of working, pushing the block back towards its equilibrium position. Now, can you kind of see up here that if I call this my plus x direction, that this should actually be considered a negative delta x, a negative displacement because it went from here and then it got pushed to the left. And this we would consider a positive delta x because it was originally here and then it got pulled to the right. So I think it's easiest if we just do the amount of it. Do an absolute value. Just do the amount of stretch, the amount of squish. And K here is going to be the spring constant. And the spring constant is just a positive value that you plug in that describes the spring. Is it a spring that's easy to squish, or is it a spring that's hard to squish? Usually it'll be given to you, but its units will be newtons per meter. And you can kind of think of it, for a certain spring, how many newtons would it take to stretch it 1 meter? Our next force is going to be the tension force. And that's going to basically be a pulling force due to a rope or a string. The abbreviation for this is going to be capital T. And the notation gets a little bit tricky here. So tension force is going to be the vector, a T with a little arrow over it. But a lot of times we might just say tension, which is just going to be the magnitude of the tension force. We don't care about the direction of it, we just want to know the amount of it. Tension force, magnitude. All right, so if a question asks you for the tension force, give a direction. If it just asks for the tension, you don't have to give a direction. The tension force would have a certain amount of pull to it, a certain force, but I can't just give you an equation for it. It really depends on the situation. But the direction of it would always be in the direction of the rope. So if I had a box with a rope tied onto it, and the rope was there, pulling on the box, then I would say that the tension force on the box is in that exact same direction.